Okay, Newton's first law stated that when the resultant force on an object is zero, it either stays still or else it continues to move in the way that it's moving. So it will continue at the same speed in the same direction. Newton's second law describes what happens if the resultant force isn't zero. And it's kind of common sense that let's say we have a car that's broken down and you push it. Um, what that resultant force will cause the car to do is it will cause an acceleration. Okay, so our car is going to accelerate. Okay, we use the letter A for an acceleration. Now, if you feel it's not going fast enough, you could get some help from a friend. They could push it, which would mean that the force would increase, the resultant force would increase. What do you think happens to the acceleration? Well, it would increase as well. That's what Newton's second law says. It says resultant forces cause the object to accelerate, and if the resultant force is bigger, the acceleration is bigger. In fact, it goes further than that. It says if the resultant force doubles, the acceleration will double. Okay, so if this was 1,000 newtons and this was 2 meters per second squared, if we doubled that to 2,000 newtons, this would double to 4 meters per second squared. Okay. Now, the other thing it says is the acceleration is not just dependent on the resultant force, it's also dependent on the mass. So let's say we were pushing with this particular force, and then we notice, okay, we've got that car going, but now there's a bus that has broken down. And we're feeling pretty confident after pushing that first car. But now what we know is the mass of this bus is much, much bigger. So if the mass increases of the object we're trying to push, what happens to the acceleration? Mass gets bigger, it's harder to accelerate it, so the acceleration decreases. And in fact, once again, if this increases by 2, this decreases by 2, i.e. it will be half its original value. Okay. Now Newton then put that all together into a nice tidy little formula, which is that the resultant force is equal to the mass times the acceleration. So let's do an example. Let's say the bus had a mass of, I don't know, 10,000 kilograms. And we were pushing with 2,000 newtons, give a resultant force of 2,000 newtons. We just put those values into our equation. And 10,000 m times A. So we then, to work out what A is, we need to divide by the 10,000. Okay, so I would say I divide this side by 10,000 and I divide this side by 10,000. But the same as kind of taking the 10,000 down and across gives us 2,000 divided by 10,000 equals A. So our acceleration in this case will be 0.2 meters per second squared. Okay, let's look at another example. Let's say we have a car and the resultant force on that car is 5,000 newtons and the mass of the car is, you know what, let's do it a little bit differently. Let's work out the resultant force. So we're going to try and find the resultant force if the mass of the car is 2,500 kilograms and we want it to accelerate at 3 meters per second squared. Okay, this is the easier way of doing it. So if we get given the mass and the acceleration, we don't need to do any rearranging. So the resultant force in this case is the mass, 2,500 times the acceleration, 3, resultant force equals 7,500 newtons. Okay, let's do a couple more examples before you listen to some questions. Let's say we have a ball of, let's keep it simple for now, 0.5 kilograms, and we're told that the resultant force on it in this direction is equal to, let's make it 100 newtons. Once again, just write out your equation. Write out your equation again, put the things in that you know. 100 is equal to 0.5 times A. We don't want to know what 0.5A is. We want to know what A is all by itself. So we divide this side by 0.5. Divide this side by 0.5. So it gives us 100 divided by 0.5 equals A. So A is 200. That's measured in meters per second squared. Okay, let's say we have, let's make it our bus again. And we know that when the resultant force on the bus is 60,000 newtons, we get an acceleration of 3 meters per second squared. Write out your equation. And that will often get you a mark in examinations, so we always make sure we do that, we don't skip that step. Put in your values, you rewrite the equation, but you put in your values. Resultant force is 60,000 is equal to the mass, which we're going to try and find out, times 3. Divide both sides by 3 to get the mass by itself. Gives us 60,000 divided by 3 equals m. So the mass of the bus is 20,000 kilograms. Now, the only way we can make this slightly trickier is the key thing in this equation is these have particular units. So this has to be in newtons. Okay, so we got something like kilonewtons. We'd have to convert it. This has to be in meters per second squared. You don't usually see it in anything else. But the mass quite often can be in different things. Particularly, it needs to be in kilograms, but quite often you might get given the mass in grams. So let's look at an example like that. So let's say we have a ball of mass 200 grams, and we want to find out the resultant force that would cause it to accelerate at 4 meters per second squared. So I can't directly go into Newton's second law with this, because for Newton's second law, this has to be in kilograms. So my first step is to convert the grams into kilograms before I use my equation. And to do that, if we're going from grams to kilograms, we divide by 1000. If we're going the other way, we multiply by 1000. So 200 divided by 1000 is 0.2, and I can then just put it into my equation. So RF equals mass 0.2 times acceleration 4. So the resultant force is 0.8 newtons. Okay, so always check and see if your units are correct before you start using Newton's second law equation. Okay, I'll break your questions down into two little sets, and that the second set will be where you have to rearrange the equation, which is slightly trickier. Work your way through those questions as much as is possible, and I'll post the answers to them next week.